Previously on Grasses and Classes. Last month, we learned how animals and plants adapt to our environment, and an adaptation is the way a plant or animal has changed in order to better survive in its surrounding habitat. Spartina alterniflora has adapted to living in brackish water by excreting salt from its leaves. It has also developed strong roots that allow it to hold onto sediment in a high erosion environment. If you remember from our first lesson, we looked at an image of Cessna Park where we pointed out signs of erosion, including the leaning telephone pole, the exposed tree roots, and the steep drop-off towards the water. But what causes erosion? What are some problems that can happen in our environment due to erosion? And finally, what are some possible solutions to restore or prevent shoreline erosion? Tune into the fourth lesson of Grasses and Classes to find out. Welcome to Grasses and Classes, brought to you by the Choctawhatchee Basin Alliance and AmeriCorps Northwest Florida Environmental Stewards. This is Lesson 4, Charting Erosion.
Hello, explorers! Today we're going to explore the causes and effects of shoreline erosion. We're going to chart the loss of land over time, and you're going to learn how to use that data to draw conclusions. Let's get started.
Erosion is the gradual wearing away of land surface materials, especially rocks, sediments, and soils, by the action of water, wind, or glaciers. Shoreline erosion is the temporary or permanent loss of sand from a shore, beach, or dune system.
Today, I'm near where Aliqua Creek enters the Choctawhatchee Bay. Looking along the shoreline, I can see several signs of shoreline erosion. Where can you see signs of erosion? Pause the video now to discuss.
We can see shoreline erosion in all of the exposed tree roots, also in the abrupt drop-off in the land. So what causes erosion? Waves, both natural and those made by boats, can increase the amount and intensity of water hitting the shoreline. This causes more sediment to move and more land to be lost. Wind can also increase wave activity and remove sediment from the shoreline. Storms such as hurricanes, tropical storms, and winter storms also cause rain, waves, and wind that contribute to erosion.
Humans can also cause erosion. How do you think this happens? Pause the video now to discuss. One example is through construction. Construction sites are usually cleared of vegetation, which leads to loose soil that can pollute our water. It also makes the land less stable and more likely to erode. Seawalls, which were initially built to prevent erosion, have been found to be more harmful than helpful. Wave energy increases as waves hit against the seawall, bounce off, causing more erosion in nearby shorelines. Another way humans contribute to shoreline erosion is by removing native plants. As we have learned, plant roots help hold the land in place, so when they're removed, erosion increases. Let's look at a visual representation about how vegetation helps hold the land in place. Let's go. Here we have 3 bottles representing 3 different shorelines. Here we have sand without vegetation representing a sandy shoreline. Here we have mulch and rocks mixed together, also without vegetation, representing a coarser shoreline. And here we have smooth cordgrass representing a living shoreline. Which of these bottles do you think will have the least amount of erosion and why? Pause the video now to discuss. Let's test our hypothesis. I'm going to pour water onto each of these shorelines. The water represents rain and stormwater runoff. Observe what's happening to the land as I pour the water over the shoreline. Which shoreline had the least amount of erosion? Was your hypothesis correct? Pause the video now to discuss.
The container with the most vegetation had the least amount of sediment wash into the water, which means it had the least amount of erosion. When we plant Spartina alterniflora along the shoreline, its strong roots help hold the sediment in place and prevent the shoreline from washing away, just like in our model.
But why is erosion bad? Why do we want to prevent it happening along the Choctawhatchee Bay? Pause the video now to discuss. Erosion destroys our natural shoreline and washes sediment into the water.
This sediment pollutes the water by causing an increase in nutrients. This leads to algal blooms, which decrease oxygen levels and can produce toxins that negatively impact underwater plants and wildlife. This sediment also makes it hard for animals to see and breathe in the water and prevents sunlight from reaching underwater plant communities like seagrass beds. Seagrass beds are important because they help prevent coastal erosion by stabilizing underwater sediment and providing habitat for animals. The loss of shoreline through erosion also means the loss of vegetation like smooth cordgrass that serves as an important habitat for many animals. Without this habitat, many of these animals would be unable to survive.
All of these examples are problems caused by erosion. So what do you think some solutions to help restore or prevent shoreline erosion? Pause the video now to discuss. The Choctawhatchee Bay shoreline is made up mostly of salt marsh habitat. A salt marsh is a coastal wetland that has vegetation that tolerates salt water. A salt marsh naturally protects the shoreline from erosion by slowing down wave energy and trapping sediment.
CBA and AmeriCorps Northwest Florida environmental stewards work to restore these salt marshes in order to protect the shoreline from erosion. In addition to planting smooth cordgrass, one of the major ways we do this is through the construction of oyster reefs. Oyster reefs are important for preventing erosion because they create a natural barrier that slows down waves, reducing the amount of sand and soil being washed away. Oyster reefs also help to reverse erosion. How do you think this happens? Pause the video now to discuss. Oyster reefs create a natural barrier that slows wave energy. This helps prevent sediment from being washed away from the shore. At the same time, sediment carried by the wave gets trapped behind the reef and helps to build the shoreline, reversing erosion. Our oyster reefs are made out of bagged oyster shells, limestone, or bagged fossilized shells. Most of our oyster shells come from participating restaurants in the Destin and Santa Rosa Beach areas. The shell is then spread out to be cured or cleaned by the sun and rain, with some additional help from wildlife like turkey vultures. After about 6 months, the shells are put in mesh bags that will become our building blocks for the reefs. Behind these reefs, we then plant native vegetation like smooth cordgrass. This vegetation holds onto the sediments that are dropped by the waves, preventing it from eroding away again. Together, the reefs and grass not only stop erosion, but actually reverse it. To plant smooth cordgrass, we place the plants in burlap bags, then fill the bags with sand. This provides a stable place for the roots to grow when we place them along the shoreline. The roots can easily grow through the bags, and since burlap is made out of plants, it breaks down and becomes part of the soil. Here are before and after pictures of a project done at Cessna Park. All of the new grass was planted by students participating in grasses and classes. Today we're going to do an activity to see how much land was lost over a 30-year time span. Those 30 years are depicted by these drawings. We will measure the width of the land that's marked by these 2 red dots. We will do 1984 together, then you will do 1994, 2004, and 2014 on your own. Today we are going to measure in centimeters because we are scientists. So we will line up our ruler on the centimeter side between the two red dots, and we want to measure about from the middle of the dot to the middle of the dot, and then round to the nearest whole number. In this case, that is 8 centimeters. Record this number in your student folder, then work together to get your other 3 measurements. Pause the video now. The measurements are 7 centimeters for 1994, 5 centimeters for 2004, and 4 centimeters for 2014. Now we need to convert our centimeters into miles, and we will do that by using a conversion formula of 1 centimeter equals half of a mile. So now we'll multiply our measurements that were taken in centimeters by 5/10. Let's do 1984 together. 1984 measured 8 centimeters, and we're multiplying it by 5/10. So 5 times 8 is 40. We count our decimal places, which is 1. So our answer is 4 miles. Now it's your turn to do the conversions for 1994, 2004, and 2014. Remember to show your work in the space provided. Pause the video now. The answers are 3.5 miles for 1994, 2.5 miles for 2004, and 2 miles for 2014. Now we need to record our miles on a line graph. We are using a line graph because we're looking at changes over time. Let's do 1984 together. Our x-axis has the dates, while our y-axis has our miles. So in 1984, we had 4 miles of shoreline. So we'll come up to 4 and make a dot. All right. Pause the video now to finish your line graph. Your graph should look like this. What does this graph tell us? Are we gaining or losing land over 30 years? Pause the video now to discuss. We lost land because the line is gradually going down. Now let's find out how much land was lost between the decades. To do this, we'll use subtraction. So to find out how much land was lost between 1984 and 1994, your formula will look like this. In 1984, we had 4 miles of shoreline. In 1994, we had 3.5 miles of shoreline. So we subtract 3 5/10 from 4. Pause the video now. That's right. The amount of land lost during the decade of 1984 to 1994 was 5/10 of a mile. So now, pause the video and do the same thing for 1994 to 2004 and 2004 to 2014. The amount of land lost between 1994 and 2004 was 1 mile. The amount of land lost between 2004 and 2014 was half of a mile. Now we need to chart our answers on a bar graph. We're using a bar graph because we are comparing different sets of data. Let's do the first decade together. From 1984 to 1994, we lost half of a mile. So looking at this graph, we have 4 lines until we get to 1 mile. That means each line equals 1/4 of a mile. So to graph half of a mile, we'll go up 1, 2 lines and make our bar. Now pause the video and finish your bar graph. Your graph should look like this. What decade had the most erosion? Pause the video now to discuss. The decade 1994 to 2004 had the most erosion. It was during this time that we lost an entire mile of shoreline due to construction and land development. Now let's determine the average amount of land lost over those 30 years. We start off by adding all of our numbers together, which was 5/10, 1, and 5/10, and we'll get our first answer. Then we must divide that answer by the total numbers in our data set, which was 3. And that will give us our average. Pause the video now to work on this problem. So to do this problem, you added your 3 numbers, which equaled 2. Then you divided that by the numbers in your data set, which was 3. And depending on how you did it, you would have gotten 6/10 and a remainder of 2, or you would have gotten 0.67. So the average amount of land lost over 3 decades was 67/100th of a mile. Well, explorers, that's the end of our lesson. I hope you now have a better understanding about erosion, its effects along our shore, and how we use oyster reefs and plants like smooth cordgrass to help prevent it. Remember, keep exploring.